By now we know that speciation can be described as a process by which you get reproductive isolation. And reproductive isolation happens because of isolating barriers. One can group isolating barriers into two broad categories. In the first category, prezygotic ones, you have different mechanisms by which mating doesn't happen, and thus you don't get zygotes. So in this case, one species mates during the night, the other during the day, and so they never meet, and thus they never mate. The second category, which is more interesting to me, is post-zygotic ones, where while in normal situations when you mate within the species, you produce viable offspring. When you're trying to hybridize, you succeed in mating, you produce offspring that are sterile or inviable. And the second category of isolating barriers is pretty interesting because there are different genetic mechanisms by which you can explain how you would end up with these hybrids that are non-functional in one way or another. One way by which you can get these isolating barriers, these post-zygotic isolating barriers, is genetic incompatibilities introduced by Dobzhansky and Muller. So in this example, we're looking at species of Drosophila, Simulans and Monogaster. In the common ancestor, you had two alleles at two different loci, HMR and LHR. In Simulans, now you have a derived version of LHR, while in Monogaster, you have a derived version of HMR. And while these two derived alleles are fully functional within their own genetic backgrounds, when Simulans tries to mate with Monogaster and produces hybrids that carry both these derived alleles, these hybrids are not fully functional, as evident here. Now, the question is, we know there are a lot of examples of these kinds of genetic incompatibilities in nature, mostly from Drosophila, but by now from different species other than Drosophila. But the question is, given a level of divergence between two different species, how many of these interactions would you expect to see? So we can tackle this question by using this very simple example. So this rectangle is the ancestral genome. A represents ancestral alleles, numbers represent different loci. So I'm just going to introduce mutations, and as I do, I'm going to keep track of the number of incompatibilities as I introduce substitutions. So when you introduce the first substitution, there's no possibility of getting an incompatibility because the allele arose in the ancestral background, so by definition it should be compatible with everything else. When you get to second mutation, there's a possibility of having incompatibility because this new allele never met the ancestral allele at the fourth locus. And with a given probability, that interaction might be a real incompatibility. So now we have two mutations, one incompatibility. Let's go to the third one. So in the case of the third one, we have one incompatibility from the previous generation. There are two possible new incompatibilities, and with a given probability, again, one of them is now a real incompatibility. I'm not going to keep adding mutations, but as it turns out, shown by Alan Orr in the mid-90s, if you keep doing that, given a linear level of divergence, you would see a quadratic response in the number of incompatibilities, hence the snowball. So the number of incompatibilities snowballs as lineages diverge. And this model has become so interesting to people that they're trying to apply it and verify it using real data from real organisms. A lot of people have done it, Moyle and Matute, so I'm just going to use the example from Matute, where they looked at 3 different species of Drosophila. And if you count the number of incompatibilities, mind you, these studies are pretty difficult to do because they have to introduce deletions and measure fitness. Understandably, the number of incompatibilities between Melanogaster and Simulans is lower than between Melanogaster and Santomia because Melanogaster and Simulans are more closely related. But what they tried to do in order to test the snowball theory was to test whether a quadratic model fits better this pattern or a linear model, and they observed that the quadratic one fits better, hence corroborating the snowball theory. Now, the problem is that as complicated as these studies are, the complexity itself makes it very difficult to study the snowball theory because there are a lot of assumptions made by the snowball theory, like if the probability of getting incompatibility is a fixed quantity, or if the interactions are static, so at once an incompatibility arises, it's not going to go away as you get new mutations. And the real organism is so complicated that you can't really answer these questions. Even counting incompatibility is pretty hard work. So what I tried to do was to come up with a very simple model, probably the simplest you can think of, in order